So we have to see the few examples related with the dipole moment and what are the application of dipole moment in this lecture. Okay. So dipole moment and molecular structure can be correlated with the help of the magnitude of the dipole moment value. Okay. So previously we have seen for the some molecules we are getting the zero dipole moment, and for some molecules we get definite dipole moment value. So there we have made conclusion that the non-polar molecule will choose the zero dipole moment. So this is, I'm talking about the dimolecular, okay, or the diatomic molecules. So if they are being non-polar, then simply we can say that it has zero dipole moment. But if the molecule is like heteronuclear diatomic molecules, so there is a certainly some electronegativity difference. So the dipole moment will be there due to the presence of some polar nature in the given molecule. So that conclusion we have made there. Now first example is the water. Okay, water. So with the help of dipole moment, how we can predict the structure of the water molecule. Okay, so water molecule, we know that this water molecule containing two hydrogen atom and one oxygen atom, with oxygen atom being the central atom. Okay, because it has the valency of 2. So this water molecule will have the two OH bonds. So we need to consider the dipole moment or the bond moment of each bond, that is each OH bond. So overall we need to consider the two bond moments of OH bonds in the given structure. So there are like two possibilities: either this OH molecule or H2O molecule can have the linear structure, okay, or it can have the angular structure. So in this diagram we are seeing this. So either water molecule can have the linear structure, this is the linear one, okay, so and this is the bent one or the angular one, okay. So there are the two possibilities where the water molecule, we are not talking about the bond angles as such here, okay. So we are just predicting whether the given structure is linear or angular one. So there are the two possibilities where water molecule can have the linear structure and angular structure. So in linear structure, what will be the expected dipole moment value? So due to the opposite nature and equal magnitude of these two bond moments of OH bonds, so one OH bond will directed in this direction, another OH bond will directed in this, one OH bond in this direction, and this OH bond will direct in this direction, okay. So due to the cancellation of the bond moments, we get the zero dipole moment, but experimentally we have observed certain dipole moment in the water molecule. So what will be the conclusion? So due to the experimental value of around 1.85 dBi, we can predict that, or we can say that it is not being the linear but it is being the angular one. Why is it so? Because if it is being the angular one, okay, it is not exactly 90-degree angle, but it might be around 105 degree, okay. But main important conclusion is what? Due to the experimental value of this around 1.85 dBi, we have to say that this water molecule is having the angular shape or angular structure, okay. And the dipole moment is, net dipole moment is resultant of these two vectors, okay. We can use the formula that we have seen, that is mu1 square plus mu2 square plus 2 mu1 mu2 into cos theta. So the cos theta can be used to find out the dipole moment of a given molecule, okay? So the net dipole moment is in the another direction, okay, third direction. So this is the conclusion we can make. So if in final we can say that this, the water molecule is having the angular structure, okay. Now next, what about CO2 and SO2, okay. Since CO2 and SO2 are having carbon and oxygen atom as central atom, so we have to satisfy the valency of carbon and sulfur, okay. So here carbon dioxide, which is having the experimentally zero dipole moment value, so we can say that it is being the linear one, okay, linear one. So this, but what about the SO2? So SO2 is being also expected to be the show the linear structure, but in actual practice we have observed that the SO2 molecule is having the net dipole moment of around 1.63 d by. Okay, so in order to prove this value, we have to say that the structure of sulfur dioxide is bent one. Okay, bent one. So the SO2 molecule which has the dipole moment of 1.63 d by. So here the individual dipole moments of the two SO bond, S double bond O, are does not cancel out each other, thus the molecule will have the angular structure. Okay, so the vector addition of the two bond moments of two SO units will giving rise to the net dipole moment of what, 1.63 d by. Okay, so the net dipole moment is in this direction. Okay, this direction. Next, what is the nature of Bf3 and Nh3 molecule? Now, experimentally we have seen that, we have observed that this Bf3 molecule is having zero dipole moment, but this ammonia molecule is having certain dipole moment. So how we can explain this? So in order to have the explanation for this, we need to say that this Bf3 molecule will have the planar shape, or the triangular planar specifically, and this ammonia molecule is non-planar molecule, because if it is being the planar one, then again also it will cancel out certain dipole moment, and this Bf3 molecule is, if it is being the non-planar, it will have the certain value of dipole moment, but experimentally we have observed zero dipole moment, so we can say that it is being the planar one. Okay, so this is the possible structure or the actual structures one. Okay, here boron trifluoride is, suppose it is being the planar one, then only this bond moment and this bond moment will be in the opposite direction and equal magnitude, so they will cancel out each other. Okay, but in the case of ammonia, it shows the certain dipole moment value which is around 1.47 d by. Okay, so due to this nature, we can say that the dipole moment of this NH bond is directing in this direction for this, and these three bonds, it is directing in this nitrogen direction, and this lone pair is being more electronegative, it will be having the net dipole moment in the upward direction. So overall we can say that this net dipole moment of 1.47 d by in the upward direction, in the direction of lone pairs. Okay, so these lone pairs will decide the direction of bond dipole moment. Okay, so ammonia molecule which has the net dipole moment of 1.47 d by, so this is explained by the pyramidal structure of the ammonia molecule. So three hydrogen atoms which lies in the one plane symmetrically with the nitrogen atom at the apex of regular pyramid, and the dipole moments of the three NH bond which is being the vector addition to, so as to contribute into the net dipole moment. Okay, so in addition to this, there is the lone pair which will also contribute largely towards the net dipole moment. Okay, so this lone pair makes the large contribution. So overall we can say that the ammonia molecule is having the contribution of three bond moments of the NH bond, as well as due to the lone pair it will show the dipole moments. Okay, now next, what about the methane molecule? So methane molecule, we all know that it is having this tetrahedral structure. Okay, but what about the dipole moment of this molecule? Okay, so we have like, certainly we are going to expect certain dipole moment for the molecule, because there is a certain some small electronegativity difference in the carbon and hydrogen atom, which is around, bond moment for this is around 0.4 d by. Okay, so methane molecule which has a zero dipole moment, this is the important statement, observed statement or the experimental one. And why is it so? Because despite the fact that being it that CH bond is possessing certain dipole moment or bond moment which is 0.4 d by, so this can be explained only if the molecule which is having the symmetrical tetrahedral structure. Okay, so this is the one important word. Okay, that is symmetrical structure. So if the molecule is having the symmetrical structure, then it will not show the dipole moment in this molecule. Okay, so each CH bond in the pyramidal or the tetrahedral structure, we can say that, so each CH bond in the pyramidal CH3 group contribute 1/3 part of the overall dipole moment. So the net dipole moment of the CH3 group is equals to nu. Okay, so this will act in the opposite direction of the fourth CH group, so thereby cancelling each other the dipole moment for each other. Okay, so overall we can say that the dipole moment of three atoms is cancelled out by the fourth hydrogen atom. Okay, next is the identification of cis and trans isomer. Now the dipole moment which can be used to distinguish between cis isomer and trans isomer. So how we can use this? So we all know that cis isomers are being asymmetrical one and trans isomer are being symmetrical one. Okay, so previously only we have seen that if the molecule is being symmetrical one, then we can expect it zero dipole moment. So here dipole moment is zero for the trans isomer because they are being the symmetrical one, and for the cis isomer, since these two atoms are on the same side, so they will pull its electronegativity towards itself, so they will show certain amount of dipole moment. So in cis isomer the bond moment will add hectory to give the net dipole moment, and in the case of trans isomer, due to the symmetrical nature and the effect of opposite bond moment, they will cancel out each other, and hence the total dipole moment of the molecule becomes zero. Okay, now next is the identification of ortho, meta and para isomer. Like previously we have seen for the ortho case of benzene, disubstituted benzene, so there we have seen that it will show the certain dipole moment. Okay, so now let us see the uh, for the other isomers also, meta and para isomers also. So benzene which has the zero dipole moment because of its symmetrical and planar nature. So now let us see the three isomeric form of the dichlorobenzene, that is ortho isomer, meta isomer and the para isomer. Since the benzene ring is being what flat and the angle between the bond is for the carbon and chlorine bond is 60 degree for ortho isomer, 120 degree for the meta isomer and 180 degree for the para isomer. So on the vector addition of the bond moments, in each case the calculated dipole moments are comes out to be around 2.6 dBi. For meta it is 1.5 dBi and for para isomer it is 0 dBi. So these calculated values will be tallied with the experimental one. So thus the above structure of ortho, meta and para isomers are confirmed. Okay, so we can obviously say that these bond angles are exactly 60 degree. Here it is being the 120 and here it is being the 180 degree. Okay, so in general the para substituted benzene which has the zero dipole moment because of its what symmetrical nature, while the ortho isomer is higher than the meta isomer. So this will provide the method for distinguishing between the three types of isomer for the benzene derivative. Okay, so these are the bond moments or the dipole moments for certain molecules. So some simple molecules like hydrogen fluoride or boron trifluoride, water. Okay, likewise various molecules they have shown for the dipole moment of the given molecules. So we can make the conclusion based upon the what we have studied so far for the dipole moments. Okay, so we can say that if the molecule is being the polar one, then it will certainly show certain dipole moment, and if the molecule is showing the dipole moment, we can say that it will show the IR spectrum also. Okay, so all we are studying this dipole moment and in detail because of the dipole moment nature. Okay, so if the molecule is having the dipole moment, it can show the IR spectra. Okay, so if the molecule is having zero dipole moment, it is being the non-polar one. Okay, like O2 and N2 CO2 etc. Okay, now next is the degree of polarity of the molecule. So depending upon the magnitude of dipole moment, we can say that which molecule is being more polar. Okay, so if there is a large difference of electronegativity, we can say that this molecule is being more polar than the other, and it will show the higher dipole moment values as compared with the other one. Okay, so if the dipole moment of the molecule is having higher value, its degree of polarity will be high. Okay, so for example in hydrogen fluoride it shows 1.91 and for HCl it is showing 1.03. Okay, so the molecule will also shows the some polarity nature based upon its structure. Okay, So if the molecule is being the symmetrical one, it will show the zero dipole moment, and if the molecule is being unsymmetrical one, then it will shows the some value of polarity and some value of dipole moment. Okay, so that is all about the dipole moment. Now next point is the polarization in the molecule. So dipole moment is quite important thing for the infrared spectroscopy, and this polarizability or the polarization in the molecule are important aspect or important concept in the case of Raman spectroscopy. Okay, so we will try to see this polarization in the next lecture. Okay?